As all things in the realm of technology does, analog connections eventually changed and are changing into digital connections of the 20th century and beyond. What I'd like to do in this nugget is talk about the problems associated with analog connections that we still encounter to this day. I'll then talk about the advantages that digital connectivity offers and how we convert an analog signal to a digital signal. Now, this is important because we still will use digital connectivity in our voice over IP realm. Digital connections are just ones and zeros, our binary communication that we use in all network connections, and we're just using a new way, meaning the IP network, of transporting that connection from one endpoint to another. So we'll look at the process of converting that analog signal to digital so that you can make a more informed decision when you choose the type of coding you would like to use on the voice over IP network, because all of them offer different advantages and disadvantages. There are two big problems associated with analog voice signaling. The first is the distance limitation. As you send analog signaling over wire, you'll have your frequencies that start out very strong and they sort of, degrade and bitter out by the time you get a certain distance away from the original source person that's talking. Now, to overcome that, we introduce these repeaters or regenerators of the signal that immediately bump that back up to at least what it was originally, and then it kind of pitters out and then regenerates and then kind of pitters out as you get further and further and further. So you have to constantly regenerate that signal. Well, anytime you regenerate an analog signal, it does regenerate the original waveform stronger, but these repeaters are dumb devices. They don't have the ability to differentiate between just white noise on the line, just kind of noise introduced through transmitting over that wire just over an extended distance, and the original voice that was sent. So the more times you regenerate that signal, the stronger and stronger that white noise gets. I don't know if you, back in the day, remember... Do you remember cassette player? Of course you remember cassette player, cassette tapes and players and things like that. I'm not talking to infants here, hopefully, but when you would copy a cassette for your friend and you would make a copy of that, it would never be quite as good as the original. And if you copied the copy of the copy of the copy, the quality would degrade further and further and further until it just became kind of this real hissy, very difficult to understand cassette tape that you would give to another friend along the way. Well, it was the same problem with the distance on here. Now, we also had wiring limitations. And I got this picture in email. Somebody sent this to me. I don't know if this is real or if this is some Photoshop thing. I'd imagine it's real, but I don't know. This is just a wiring mess of telephone wires that is somewhere in some I think they said this was India, but I don't know. Maybe somebody in India can email me and let me know if they really have places like that or not. But this is just the wiring requirements for analog. For each call, analog requires a tip and a ring wire. So 2 wires to come in for every single one. If you used analog signaling for an entire area, like a neighborhood, or maybe you have a business here with 100 phones inside and you had analog connections for all those, you just have this mob of wires that were coming into the business. And the wiring requirements just became out of control for analog signaling when you had a bunch of those connections coming through. So we had to have a way to send more than one call over a wire, which analog signaling just could not do. That's where digital signals came out. What digital signals do is convert these electric signals, the waves of electric signals, into zeros and ones. So when you do that and eventually send analog signals in digital format with just zeros and ones, you eliminate the distance, because as long as you have a method that can accurately communicate a 0 or a 1 over any distance, I mean, as long as that method doesn't mess up the ones and zeros, you should be good to go. And we have connectivity methods nowadays, whether it's T1 lines or whether it's voice over IP, or there's many different ways that we can send a 1 or a 0. I guess you could even get down to what is that? Where they tap the little wire. It's like beep, 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 beep. You signal SOS. Oh, what is it? Now it's gonna bug me. Beep 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 beep. Anyhow. you know what I'm talking about. You're probably saying it right now, and I can't hear you. My analog signal is too weak. So this tapping system, I'm going to figure out what that is another way you can just transmit ones and zeros or ons and offs over a wire. Any way that you can do that, you can go over any distance as long as you accurately convey your ones and zeros. Likewise, once you convert an analog waveform into ones and zeros, we have methods of sending multiple streams of ones and zeros over a single wiring. That's where digital conversion and digital communication really outdoes analog signaling. So if digital signaling solves the problems associated with analog, then we should understand how digital signals take an analog stream and convert it to ones and zeros, or essentially that means digitizing voice so that we're able to send it in ones and zeros and accurately understand it over at the other end. To get into this, we need to understand a famous historical figure, and that is Dr. Harry Nyquist. This is a picture of Dr. Harry down here, and he is quite the famed person in the telephony industry because he found a way to take an analog signal and send it digitally accurately and reconstruct it at the other end. Here is his theorem, or his formula that he uses. He says, if you can sample at twice the highest frequency, you can accurately reconstruct a signal digitally. Now, that's quite a mouthful, so what does that mean? Well, when you're sending a signal through analog, there's frequencies, and that's kind of the voltage level as it goes up and down and sends electronically over any kind of medium. What he's saying is if you take the highest frequency, right here, whatever the biggest peak is on there, and sample at twice that frequency, you can reconstruct it digitally. So let me give you some examples. There's some common frequencies that are out there. Like the human ear can hear between 20 and 20,000 hertz. So if the maximum up here was 20,000 hertz, that's about the maximum our human ear can hear. Now, human speech comprises between 200 and 9,000 hertz. So when we're talking, our speech level will kind of vary between 200 and 9,000, and our human language and our voices can't really communicate in any frequencies outside of that. Now, let me talk about if we were to sample that at twice the highest frequency. What does that mean? It means if I were to take time, and this is voltage over time. If I were to say this is 1 second of time, the Nyquist theorem says if you were to sample that at twice the highest frequency, if I were to say, let's take samples, at twice 9,000 hertz, that means I would take 18,000 samples. A bunch of 18,000 of these samples over this frequency as it's going along, and every single second, I would be able to accurately reconstruct human speech exactly as I hear it coming out of somebody's mouth. And you can see right below that I have the Nyquist theorem, which samples between 300 and 4,000 hertz, because Nyquist said, you know what, 18,000 samples is just too many. We need to have a level of frequency that allows us to get, somewhere a decent number of samples that we can accurately reconstruct human speech so that you can hear it when we're sampling it, and understand it as we sample it digitally in ones and zeros. So his theorem says if we sample human voice, 4,000 hertz, 8,000 times a second, as it goes over this little thing. Every second you sample it 8,000 times, that should give us enough ones and zeros to accurately reconstruct it. Once we have sampled the voice 8,000 times a second, we can then line that sample up to a quantization scale. Now, quantization is a word that will impress your friends, first of all. If you're just talking in general conversation, be like, yeah, I'm going to do some quantization this evening. They'll be like, wow, that sounds sophisticated. What it is it's a way of lining those samples up to some kind of scale that you can represent them with. Now, you'll often see quantization represented like this. If you're ever looking at documentation, you'll see lines being drawn through this signal like this as it goes, and they're much straighter than my lines. But each one of those lines represents a sample. So you figure if you were taking this in reality, there would be 8,000 of those lines every single second, and each one of them would peg a certain point on that analog signal, kind of like those little dashes I was drawing in the previous one. Quantization involves taking that mark that you put on the signal and lining it up to some value that you can represent that with. Now, the initial step 2, quantization, is taking the value of the amplitude, let me just write that down, of that line. So, there's a scale, and this process is known as pulse amplitude modulation. There's a PAM scale out there where you can actually take the voltage of that line, or the amplitude, and line it up to a specific value. Now you notice on my lines here I have a bunch of little tiny close together lines, and as it gets further away, they actually get further and further apart. These are known as the segments. This is segment 0, segment 1, segment 2, segment 3, and segment 3 going up here, and so on and so forth as we get further away from the bottom line 0 of this graph. As we go down, we go from segment 0 to segment -1, segment -2, and so on and so forth. This is how we chop up the voltages of electricity. Now, there's only so many samples that you can take using this pulse amplitude modulation scale. So what we do is take mini samples at this, this should be 0 right here, at this very close to the bottom line, and take fewer and fewer samples, or I guess space apart the samples further and further away as we get further up on the voltages. The reason that we do that is because it gives us a more accurate level of quantization in most of the range that human voice speaks. When you're speaking with human voice, like take my scale like this, you can see that, most of the time I'm going to be up here, and, if I get really loud or really high pitched, it's going to kind of, shoot way up, way down, sorry, Harry down there, and shoot way up and way down. But most of the time, most of our conversation is right around this close to the line or close to the 0 scale that we can. So by taking more samples, all down here, we can get a more accurate reading, or I guess you could say more accurate quantization level with each one of these lines than if we would just space them out evenly. So I guess you could say the louder and more flamboyant you are on the phone, if you get really loud and very much outside of the voltage scale, the less accurate the representation of your voice will be on the other side. So this process, known as quantization, uses the PAM scale to line up all of these samples with a specific level of voltage, either positive or negative. Once we have the signal quantized, if that's a word, I may have made that up, but once we have quantized the signal into these electrical values, we have to convert that to a binary number, because we can't send electric values, we have to send ones and zeros over the line. This process is known as pulse code modulation, or PCM. So you take all those sampled values, you came up with all these electrical levels over here, positive or negative, and you convert them into binary numbers. Now there's 2 PCM methods that we use. One is known as A law, one is known as mu law. It's a Greek or Latin character, I don't know which, but it's a representation, I believe it's Latin, of how we convert that together. You'll often see it, since we can't type this on a keyboard, you'll often see it written as mu law, but it should actually be mu. It's pronounced mew like a cat. Let's all say that together. You ready? Mew. It's kind of fun. Mew. So the 2 different methods are 2 different ways of encoding that electric signal as a binary number. Now, A law, well, I'll start over here with mu law. The way I remember it is based around this. Mu law is used in the United States of America and Japan and Canada. There's actually 3 countries that use the mu-law-Ford method of encoding. A law is used in another place other than the United States, Japan, and Canada. A law makes more sense when you look at it. Here's the way A law works. A law takes this binary number to represent positive or negative. If this is a 1, that means you're up in this positive scale. If it's a 0, that means you're down here in the negative scale. So this, you could just think, represents pos or negative numbers. The next 3 binary digits that you have right here represent what segment you are. Remember I said that over here in electrical signaling they divide all of these amplitudes, which is how high up on the voltage scale you are, into segments and take more samples at the lower segments than they do at the higher segments. So this is segment 1, segment 2, 3, 4, and so on. They do 7 in each direction. Then down here you have 1, 2, 3, 4. These are the different segments that you have, the values there. And then this is the interval in each one of those segments. So that's the individual numbers in each one of those segments that you have. So A-law, in my mind, makes a lot more sense because 1 is positive, and then you have the segment value. So if you're segment 1, it'll be 001, 0010 for segment 2, binary to decimal conversions there. And then what number you are in there is the actual interval. Mu law is exactly the opposite of A-law. So, for instance, where A-law says that this 1 is positive, 0 is negative, U-law or mu law says 0 is positive, 1 is negative. Where you have segments being 1, 2, 3, 4 here, mu law does exactly the opposite. The best example I can give you of A-law versus mu law is if you've worked with access list, which if you've gone through CCNA, you've seen access list. You know what the subnet mask is, right? Where you have like a subnet mask of 255, 255, 00. Well, in access lists, you don't type them in that way. You type them in with the wildcard mask. And wildcard mask is exactly the opposite of a subnet mask. You do 00255.255. Now, why they did it that way, no idea. I'm sure there was some mindset behind that going, okay, these are match bits and blah, 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 blah. But that's how you have to learn access lists is exactly the opposite. OSPF configuration, working exactly the same with your matching bits. This subnet masks is like A-law. It's kind of like, oh, that makes sense. Wildcard masks is like mu law or U-law because it's exactly the opposite of the A-law. So again, it all depends on what country you're in. If you have, and the point behind this is if you have, let's say, the United States, there's my rendition, communicating with, we'll say, Europe, you need to convert your voice coding from one end to the other as you can communicate those digital values. Cisco routers can do that. It's known as transcoding those voices back and forth because they do use different coding standards. Once you have the voice converted to binary, you can then send it over a digital line. Now that could be a T1 line or an ISDN line like we're going to be talking about in the next nugget, or a voice over IP network, just like our data that we send from our computers. 1s and 0s is all we send across the network. But that can take some bandwidth. You figure, think about this, and this is, I love this part right here. Check this out. You figure 8,000 samples every single second, right? How many bits are in each sample? 8. Each bit or each sample is turned into an 8-bit binary number. So if we take 8,000 samples times 8 bits per sample, we end up with 64,000. And that is how we get each voice call coming from a PBX system consuming 64 kilobits per second, or 64,000 bits per second. That's been the standard for digital voice for years, and it's always been assumed that you always have to have 64 kilobits per second per voice calls. But we can optionally compress the samples, because if you think about it, I mean, you got that analog signal going like this. Whoops. Like this, up and down, up and down, up and down. If you're taking 8,000 samples, that's a lot every single second. Each one of those samples are probably about the same. Like for example, if I were to say the word cow, it takes about a second to say that word, right? Cow, cow. So if I were to take that word and sample that 8,000 times, the chances are most of those 8,000 samples are going to be almost exactly the same. I mean, you got the initial sound, and then it goes for a while, and then I go ooh to get the W at the very end. They sound almost exactly the same if you were to split those into 8,000 individual sounds. So you can optionally compress the samples to consume less bandwidth. So Here's what you can do. Send all the samples. That's what we've been doing up till now, and that's what consumes 64 kilobits per second. Or you can send just the changes in the samples. For example, if you've got, first sample looking like 110000101, next sample is identical, and then maybe the next sample after that goes to a 1000110, goes up by 1 or something like that. You can just say, okay, we did a +1. Send just the changes, consuming less bandwidth between those. Or you can do what some of the modern methods do, which is build a code book. Now, what the strategy is in this is that each side, as you send the voice across, has a code book that it builds for human voice. And human voice, I know it sounds like, wow, there's a lot of changes. Just listen to my voice as I'm speaking. It sounds like there's a lot of changes in my tone and fluctuation as I go up and down, but when it comes down to it, not really. There's only so many frequencies human voice can consume. So what it will do is the router on one side and the router on the other will build a little code book digitally that says, okay, well, the E sound commonly sounds like this. The F sound commonly sounds like this. And it kind of comprises a human voice code book. And as it starts sending voice, it sends codes that represent your voice that consume less bandwidth than the actual voice if I were to send all 8,000 samples every single second going across the wire. A common compressed value that does that is known as the codec G.720 line. G729 consumes 8 kilobits per second versus the 64 kilobits per second that our normal voice has, and really, you can't tell the difference. At least I can't. I don't have a very sensitive ear, I guess, but I cannot tell the difference between somebody sending voice at 64 kilobits per second and somebody sending it with this compressed format using 8. So that's some of the advantages that we get by using voice over IP is we can send voice using a lot less bandwidth than we could in the typical voice world. So there is our part 1 of how digital communications work. Essentially, we walk through the problems with analog connections, which again were the distance limitations because you had to regenerate the signal, and the amount of wiring that it would take. Now, this nugget was dedicated to answering the solution to the distance limitation. Because if we can convert our analog voice into ones and zeros, then you can send those as far as you want using whatever method you can communicate ones and zeros with. The next nugget, we're going to talk about how we got over the wiring issue by sending multiple calls over a single wire, and that's where we get into our T1 and E1 lines that group together multiple connections. We then looked at the second major section of this nugget, which is to convert the analog signal to digital. And we do that using the Nyquist theorem, sampling at twice the highest frequency that we're looking at. Now, one more thing I should mention, the Nyquist theorem samples up to 4,000 hertz, right? Human voice goes up to 9,000 hertz. So the Nyquist theorem saves some samples, because otherwise we'd consume a lot more bandwidth than 64 kilobits per second by sampling 18,000 times per second. But it eliminates some of the quality of our voice. That's why over an analog line, over a voice conversation, you can always tell the difference between that and talking to somebody in person. For example, you notice if you ever listen to the radio, like an FM channel, you'll hear, the radio host talking, and they'll say, let's get our caller on, and then you can notice a significant quality difference between the radio announcer and the person on the phone. They have a quote-unquote phone sound to them. That's because you're only digitizing enough of their voice to give you recognition so you can tell who that person is, and to give you the ability to understand their mood. That's what the up to 4,000 lets you get, but it doesn't give you the full fidelity of an actual voice, which is, you can tell me when I'm talking to you now, I sound a lot better than if I were talking to you over the phone, because CBT Nuggets samples at a level much higher than the typical voice call. So one more thing I wanted to plug in there as we wrap things up. So that is converting the analog to digital signal. I hope this has been informative for you, and I'd like to thank you for viewing.